Nice to see you. Oh, great that you made it in time.
Great to finally be here. I've seen this place since it was construction.
Okay, fantastic. Yeah, you get to see the finished product now.
Yeah.
Give you a tour later.
Great. The car on the left. Good morning, sir.
Hi.
Nice to see you.
Feeling okay, jet lagged?
Sorry?
Are you feeling okay from the travel?
I've been in California for a few days, so
Oh, you have, okay.
it's 3 hours. between-
Welcome, anyway.
So weird used to.
So, okay. Welcome, everyone. So thank you, Andrew, for supporting Carlos' visit. Carlos is a friend. He got his PhD at the State University of Campinas in applied mathematics, if I'm not wrong. I was his co-supervisor. And he did a brief postdoc of 1 year in Hong Kong under Ravi Ramanandam. And now he's back at Campinas. I just got the news that in the next month or two, he will move to spend a year in Paris, in Sorbonne, working under Marco Tullio, in Marco Tullio's group there. So yeah, so Carlos, thanks for accepting the invitation. He's going to talk about Bell nonlocality with arbitrary relaxation of parameter and measurement independence. Carlos, floor is all yours. Thank you.
Thank you guys for being here. So I think I will need to change here, but I use the
Yeah.
You will.
There's no, the laser doesn't work on the
doesn't
screen.
work. Okay.
It's the pointer on the screen.
Okay, maybe I use my hands and
Exactly.
exactly.
Except that the people on Zoom won't see that.
Yeah. So it's a joint work with Ravi when I was there in Hong Kong, doing the postdoc, and with Fabien Cabel. The work was published in HCon last year, mid of last year. And I would like to start giving kind of a short review on Bell nonlocality. Most of you might have heard about it, but I think as the work is really connected with the ideas of the hypothesis of Bell's theorem, I think it's interesting to review it a bit. So in a Bell experiment, it's a type of experiment like this, where you have a source in the middle and you have two experimentalists, Alice from one side, Bob to the other side. And then this source is producing two physical systems and sending one to Alice, another one to Bob. So represented by these purple balls. And then Alice and Bob, they will select a measurement and perform the measurement in these physical systems. I'm just labeling this measurement by X, but must be whatever measurement they want. And they get the result of this measurement. And there is also this hypothesis that during this process, Alice and Bob, they cannot communicate with each other. They are not allowed to communicate during this whole process of measurement and get the results. And okay, and the idea is that they repeat this process several times, and collecting the data will be the measurement that they choose and the result of the measurement. And then they get together and share the data, and with this data they can infer some probability distributions, especially they can infer this type of probability distribution here, which will be the probability of the results of Alice and Bob given the choice of measurements of both. So, and you say that you do have a local hidden variable model for these distributions, probability distributions, when you can decompose it by an equation like this one in the right. And what is especially about it is that you can see here that over the knowledge of this extra variable here, the lambda, now Alice and Bob are not correlated anymore. They are independent from each other. And the idea is that over some assumptions, you do expect that every type of probabilities, conditional probabilities should have this model. However, when you do this experiment using quantum resource, you find some probability distributions that do not satisfy this model. This is kind of the idea of Bell's theorem. But I want to go a few more in details of what are the hypotheses behind these local hidden variable models. Or in another way, why you should expect that the probabilities should decompose like this model, or over what type of assumptions this should be true, or we should expect that this is true. And first of all, it's a hidden variable model in that this is not like a hypothesis, because you can always, mathematically, you can always do such a decomposition like this. You are just adding an extra variable here, and this extra variable, this is, I think, is law of total probability, and here is just Bayes' theorem. You can always do this kind of thing, but and then you have a kind of a model, a hidden variable model. And but the idea of this extra variable that you add is that this extra variable here should be the variable that are considering the whole common past of Alice and Bob. This variable should explain any type of correlations that Alice and Bob have, any type of interactions that they do have in the past of them. So kind of want to choose this variable for us to describe to put in the model. And with this description, you might say, yeah, but how can you know what type of interactions, all the type of interactions that Alice and Bob might have in the past? This is complicated, but kind of the idea is that you might not have complete knowledge of this variable. You consider all models without knowing exactly which variable should be this one. Okay. So now a real hypothesis is what they call by measurement dependence, and it is given by the idea that the choice here of the measurement of Alice is independent of this extra variable, the hidden variable, or the common past of Alice and Bob. And the same for Bob. The choice of measurement here is independent of this common past of both. And mathematically, you can express it by an equation like this. So this variable lambda is independent of the two variables x and y of the choice of measurements. And okay. And usually people call about this hypothesis as free will or freedom of choice, and has this idea that Alice and Bob might be free to choose whatever measurements they want to perform, and free in the sense that it's not correlated or predetermined by anything in the past of them. More or less the idea of this hypothesis. And you might ask, how can we guarantee that this independence is true? And I think the answer is you can never do it, for sure, but you can find you can perform this experiment in some ways that would be quite unexpected that these correlations exist.
Carlos, can you go back a slide, please?
Uh-huh.
Yeah, so I know that this formalism is kind of a little bit blind to causal relations, right? So, but can you guarantee from this definition that, because here you're saying that lambda given x and y is equal p lambda, right? It is as if lambda was independent of x and y. So can you guarantee the opposite from this equation, that p of x and y given lambda is equal to p of x and y? So
I think it's a if only. If this is
Okay.
true, it
Well,
will be true and it will change.
That's cool.
I mean, it's not because he hasn't introduced a P of X and Y yet,
Yeah.
right? So
Uh-huh.
you can approach this question and say, oh, there is a P of X and Y, I choose them randomly or something.
Mhm.
Or you can just say, no, I'm going to do everything conditional on X and Y. And if you say the latter, then you can't say what you suggest.
I know. Yep.
So, and I was saying, how can we guarantee this independence? I think it's, in some sense, can never do it, but you can do this experiment in a way that would be super weird that you have strong correlations between these variables. I think my favorite one is this. It's not that practical, but I think it's nice. And the way they do it is that they perform some measurement in photons coming from stars in microwave far away from each other. And they select the measurement here to perform based on the result of this measurement in this photon. So in some sense, it would be super weird that you have correlations between this common path of Alice and Bob, like the source that is producing the physical system, and I don't know, maybe the devices are kind of produced for the same company or something like this, but still it's super weird that you have strong correlations with a photon far away, right? So, although it might be the case, I don't know, but would be quite surprised. Okay, now another hypothesis called parameter independence. And the idea is that you are assuming that the choice of Alice here is not affecting anything on Bob's side. And the same for Bob. The choice of measurement of Bob is not affecting anything in Alice's side. And this should be true even given the knowledge of the hidden variable. It's a little bit different from non-signaling in this sense. So mathematically, this hypothesis expressed by these two equations here. It's basically saying that this is the margin Alice's probability distributions, and I'm saying that it does not depend on y. It's the same regardless of the choice of y. It's this idea that what is the choice of measurement of Bob is not affecting at all the behaviors or the probabilities on Alice's side, and the same for Bob. And usually people refer this hypothesis here as locality. They have this idea that if they are far from each other, if this is not true, you should have some action at distance somehow. And again, you can make kind of the same question. How can we guarantee that no communication takes place here? And one more time, I don't know if it's ever possible to do it, to guarantee it, but what you can do, it's do the experiment in such a situations that would be quite of weird that you have this communication. One way to do it is, it's do the experiment such that the measurement process here on Alice's side is outside the light cone of the choice here of measurement on Bob's side. So if the some communications come or some influence comes from the choice of measurement here of Bob, to make any difference here on the Alice side, it should travel faster than light. And you do expect that this doesn't happen, but I don't know, it might be. And it's a bit subtle that this not necessarily violates relativity principle, but still people believe, some people at least believe that this communication should not be the stuff who is failing or something like that. Okay. And the last one is outcome independence, the next hypothesis. And it's similar, but now the idea is that the outcome of Alice here is not affecting where Bob is seeing in his side and vice versa. And mathematically, it's expressed by this expression here, like that the A does not make any difference on both sides of what is he's seeing in his distributions, probability distributions, and this is equivalent to say the same for Alice as well. The same expression. If this is true, will be also true. But I think I prefer this formulation of this hypothesis, this one here, that if this is true, will be also true that you can find a different variable here, such that Alice and Bob distributions are deterministic. And people associate this with the idea of realism, that you know for sure, I mean, if you perform these measurements, some measurements in a physical system, this result is already exists before you perform that measurement. It's deterministic in this sense. And so this is one more of the hypothesis. And okay. And then when you get together these three, it is MI, measurement independence, outcome independence, and parameter independence. They together lead us to the local hidden variable model. Okay. However, now, if you go to perform these experiments using quantum theory, how can I do it? You can have a source here producing entangled states, send one part of it to Alice, another part to Bob. Then they perform some good measurements on it, quantum measurements, and get the statistics. And for good choice of states and measurements, they can get to some statistics that you know for sure that cannot be decomposed in the local hidden variable model. And you can do it even that if we perform the experiment with the space-like separation, so it would be weird. I mean, if you it would be weird that communication is taking place. You also do it in a way that this measurement here was randomly select. And you also expect that there is no correlation between the source here and the choice of measurements. And if you take all this amount of care, still you do not have a local hidden variable model. So, and basically this is what they call by Bell's theorem. It's a different way to formulate it, to say that quantum predictions, or these statistics that you can get with quantum theory, are in disagreement with local hidden variable models. But as you see, you can decompose these local hidden variable models in these three hypotheses here. Then quantum predictions are in disagreement with these joint three hypotheses. And of course, if you get to this point, natural question will be, can we identify which assumption, or maybe more than one, fail? And so I think nobody knows the answer for sure. Some people believe that one, some people believe it's another, but no one's have an answer that I don't know if that you can prove that indeed this is the assumption that is failing. And one way to see it, I think that the easy way to you could test to find which one is failing is just assuming two and do not assume one of them. But if you do it, you can now recover quantum predictions. You create a model that is more powerful than the local hidden variable model. And this model will be powerful enough to recover all predictions of quantum theory. So this naive way to try to find which one is the hypothesis who is failing doesn't work. And okay, so this kind of review. And in our work, what type of questions we were trying to answer was that, what if we only partially assume some of these assumptions or hypotheses? Instead of assuming completely, what if you relax that hypothesis a little bit and see what you can get? And for it, you need to start to create some definitions to say what would be relaxations of these assumptions, and perform some choice. And for parameter independence, these two equations here were not exactly the one that I showed before, but are equivalent to it, just saying that the choice of measurement of Bob doesn't affect what Alice is seeing on her lab, and the same for Bob. And if you want to relax it, you can do it in some way like this one. Okay. When parameter independence is true, these two are equal for our choice of A, X, and Y, and lambda. But now, instead of asking for these two be equal, I will put a bound of how different they can be. This is the total variational distance. So I'm kind of putting a bound in the distance between these two probability distributions. And again, the same from Bob's side. So you are performing a relaxation of that hypothesis, and the parameter that you have to establish the amount of relaxation is this epsilon here. And when epsilon is equal to 0, so the distance between these two probabilities is 0, so it's kind of it's the same. And here as well, so you come back to the parameter independence hypothesis. On the other hand, if epsilon is equal to 1, then it's the maximum value that this distance can have. So you're not putting any hypothesis, it can be whatever. And it's also, when this is the case, you need to have signaling between the parts in all the rounds of the process. So, okay, so this is the idea of relaxation. You are adding an extra parameter here, saying how much of that hypothesis I'm assuming or not, based on this parameter.
Excuse me. This equation is valid for any choice of
Any choice.
Y, X.
Yes, yes. It should be true for any choice of A, X, Y, and lambda. Okay. So this was the relaxation of parameter independence. And now for measurement dependence, here I put in the different way. Saying that when you have measurement dependence, this equation should be true. And for me, I think it's equivalent, but you can discuss it if it is not. And the way that you relax it is a little bit different. And it's based on this idea here. You put the bounds on how much this distribution can be. And the idea that if this bound is given by some expression here, then this distribution will be uniform, and you cannot have correlations between this choice and this one. On the other hand, if this bound is kind of trivial bound, you can have here whatever type of probability you want, and you can have complete correlation between the hidden variable and the choice of measures.
Just for clarification here, so this is assuming that you are choosing X and Y by some process that you have good reason to believe is uniform.
Yes.
Flipping coins or something.
Yes. Yes. And okay. So now that you have these two relaxations, you can create a new type of model, not anymore the local hidden variable model, but a model with the relaxation of that hypothesis. I didn't comment so much, but in this presentation, at least, we will always assume outcome independence, and you just do relaxations of these two hypotheses. But in our work, we also deal with the other situation where you assume these two and relax this one. It would be nice if we could relax the three of them together, but we still don't have one result on this direction. But okay, so the type of model we want to consider is like this. It's a hidden variable model, and with outcome independence, this is one of the assumptions, and with relaxations of measurement independence and parameter independence. So we can decompose the probabilities in such a way, but with some restrictions on these guys here. And then you can ask how much relaxations of this hypothesis are required to recover quantum behaviors or quantum statistics. And what you have proved is that even if you jointly relax measurement independence and parameter independence arbitrarily, but not completely, if you relax completely, for sure you can recover all quantum predictions that I told before. If you remove one of them, one of these three, you can recover all quantum predictions. However, if you jointly relax these two arbitrarily close to the maximum amount of relaxation, you still do not recover all quantum predictions. You can find some quantum experiment that could not be described by this model. This is basically the main result, and I try to give an idea how you get to it, and the idea is close to most of the proofs on Bell's non-locality stuff, that you find a task and then you see some bounds of how quantum theory performs on this task, how local hidden variable models perform this task. In this case, you also consider how our model, that are these relaxations of the hypothesis performed in this task, and then at the end you show that quantum performs better than the others. So for sure, as quantum is performing better, you cannot describe quantum theory by this model. The idea is this, and what you need to do is first find a good task for it, and then to find what are the performances of these models on this task. The main idea is this. And for this one, I start reviewing this Hardy paradox. It's a paradox in this kind of experiment, an experiment where Alice and Bob, they just have two measurements. They performed only two measurements, and the outcomes are dichotomic. So just a bit here. And then you can prove that if we assume the local hidden variable model, so this kind of decomposition for our statistics, but if you also assume some what we call by Hardy zeros, and that is just that for some measurements there are some results that never occur. So the probability of this result 0, 1, given the measurements was 0, 1 is 0, so it never occurs. And similar for this 2, 1. With these two assumptions, you can prove that this other probability here must be 0 as well. This was done by Hardy a long time ago. But what is interesting is that he finds that if you perform this using quantum resource, I'm not going details, but it's a special state here and some good choice of measurements, and the statistics will be given by Bohr's rule like that. But if you do it, you still satisfy the Hardy zeros. So the probability that I want to be 0 will be indeed equal to 0. However, the other one that was a conclusion of local hidden variable hypothesis, and there's 3 zeros here, now is not 0 anymore. It's a little bit bigger than 0. So this is, for instance, is one way to prove Bell's theorem, to prove that there are some quantum statistics that are not doesn't allow have the local hidden variable model. And you kind of get inspiration on this, but this was not enough for us. I think mainly because this, although this is bigger than 0, it's still small. So if we start to perform some relaxations of the model, this new type of theory will violate this amount here fast. So Hardy was not enough. And what to...
Can I ask a question,
Yeah.
Carlos? Should your theory depend on what the value of P is? Is this like the minimum you can get by putting P close to 1?
Do you mean this?
Or your epsilon parameter, right?
Oh, yes, it depends on the epsilon.
Yeah, okay.
Yeah. you will see this in some slides. And so, okay, this is hardened, and it's not from this year. This is the number of the paper. And as I told this, you need to have a more strong task somehow to be able to do what you want. And to do it, there is this kind of generalization of the Hardy, they call it parallelized Hardy paradox. And it's quite similar. Again, LSM objects have two inputs, two measurement choice, and the measurement results now will be bigger, will be a bit string of size n for each one, where n is a parameter now that you can change. And I will describe the probabilities by this notation here. So it's the first bit of Alice, the first bit of Bob, and so on and so forth. And you can also prove something similar. Now the Hardy zeros will be a bit more general, but the idea is that it's almost as before. Before you would remove this part here, you would ask for this probability here to be 0. Now you ask that anytime that one pair is 0, 1 for this choice of measurement, this probability must be 0, whatever are the other values here. And you do kind of the same here for the other original Hardy zeros. And what it is the p Hardy now, so what is the quantity that you want to see how much it is. It's a bit more general as well, but it's basically the same idea as this, but making the sum of everyone. Before, what was 0, what the p Hardy was when one pair was 0, 0 for these measurements. Now I'm asking for at least one pair be 0, 0 and do the sum. And for this paradox, you have something similar. So if you have a LHV model and now these zeros in the probabilities, you can prove that the p Hardy, that was that sum of probabilities, is equal to 0. And however, with quantum, you can't violate it. And the way to do it, it's simple. It's again, it's kind of performing the Hardy paradox, but in parallel. It's not in parallel because you always use the same measurement here, but it's performing a lot of Hardy paradox. So the same state, the same measurements, and doing it, you can show that the p Hardy will be close to this expression here. And what is interesting in this expression is that when n goes to infinity, when n is quite big, this quantity here goes to 1. So the local, when you consider local hidden variables, is 0. When you consider quantum, goes to 1 as you increase the size of n.
So then you're saying when you take your sample to go to infinity, you're almost like freezing the result of these boxes into one of these two boxes into one of the results, right? The results given by this pH. Is that it? This might be because I'm trying to connect with like quantum Zeno effect in the mathematics of the thing, right? So n goes to infinity, you know for sure the result of the box is that pH there.
So I don't know, because kind of, because this is a sum of.
So no, yeah, this sum.
Yeah.
Is the sum that's going to 1, right?
Yes.
So if you assume these Hardy zeros and local hidden variable model.
You know for sure that never occurs. But quantum always goes to always happen. Okay. But again, what you want to compare is not with local hidden variable models. You want to compare with these more powerful models where you have relaxations of two of the hypotheses, and you want to find how good can be how good you can perform this task on this more general type of statistics that go with this model. And I'm just showing the results. It involves a lot of calculations. This is the hard part of the paper. But you can prove that assuming, again, hidden variables and outcome independence and relaxations of parameter dependence and measurement independence, you can get a bound, again, sorry, also the Hardy zeros. You can get a bound for the P Hardy, which is given by this expression here, 2 epsilon minus epsilon squared. And you can see it does not depend on L, which is a bit weird, but I think it's more like, at least geometrically, make a little bit of sense for me. But just depending on the epsilon here, and to have this bound. And
Sorry, is this kind of cancellation into derivation? Or if you change something, it will appear again?
sorry,
L independence.
Notice that L has to be strictly greater than 0.
yes, there is this.
So if you set L equals 0, then you get no bound. It has to be, but for any non-zero amount, which is slightly strange.
Okay. I'm just doing the plot of this function to have an idea how it behaves. And for us, what is important is that it's increasing here, it's going to 1, but it's always smaller than 1 if epsilon is also smaller than 1. And you get our conclusion with this. So now I'm comparing here these 3 models. So for this task, this parallelized Hardy paradox, the P Hardy for local hidden variable models is 0. For the quantum model, it's close to this expression here, and what is important for us is that it's getting closer and closer to 1 as n increase. And on the other hand, for our relaxed model, you have this bound here, and as you can see, this quantity do not depend on n. N is always, if epsilon is smaller than 1, this quantity is always smaller than 1 as well. Also for L bigger than 0. So regardless of the choice of epsilon and L, if epsilon is smaller than 1 and L is bigger than 0, this quantity will be strictly smaller than 1, and I can find n big enough such that the quantum is bigger than the maximum of this model. And the conclusion is that for sure, for this specific quantum statistics, you cannot have a model like this one here. Okay? And kind of the idea of the proof of the result, you can always find quantum predictions that cannot be explained by this model here for regardless of the value of L, if it's bigger than 0, so if it's not complete relaxation, also regardless the value of epsilon, if it's smaller than 1. So again, if it's not complete relaxation. And is it? So take away home. Again, kind of this is Bell's theorem. Quantum predictions are incompatible with disjoint assumptions of measurement dependence, parameter independence, outcome independence. No one knows. Some ones prefer one or another, but as far as I know, no one's have a sure answer for which of these 3 hypotheses are not satisfied, or maybe it's more than one is not satisfied, but no one knows exactly which one. And as you see, if you remove one of them, you can recover all quantum predictions. And what we have done is that, okay, I'm not removing completely, but I'm relaxing it. And even that you arbitrarily relax it, you can still do not recover quantum theory, quantum prediction. So you need to indeed remove a I mean, if you're assuming this one, you need to completely remove at least one of these two to recover quantum predictions. And it's it. Thank you.
Yeah, thank you, Carlos. I think that we have at least one question here from the in-person audience. So, Matt.
Last couple of days, I feel like I'm asking all the experiments as questions. So, I'm wondering about what happens if you consider the feasibility of actually proving this experimentally. So you've got two issues. One is detection efficiency. So then you get a detection loophole, but also even if you can close the locality loophole, since you're using the same input for all these parallel repetitions, you have to be able to do n runs of the Hardy paradox, all at space-like separation from each other. So there's going to be some limit. Ephraim would know more about how many times you can run it and still be at space-like separation. So do you know how what are the requirements there to actually prove that this result is you need to.
Good. This in the paper you kind of do this first part, and here I just bring it the simple one, but you also have an inequality version of the result, because here you have hard zeros, and if you do experiment, this is never it's impossible to satisfy. So you remove these zeros and still have a inequality version of the result, which also works. So you kind of avoid this problem. But again, it still needs, you have a table to show how much you can relax, given the necessary number of copies, given the value of epsilon. But you are writing by the moment another paper, which is with people who are doing the experiment. As far as I know, you were not able to do it loophole free, but they try to do it in several different, it's like 4 different groups performing the experiments. One of them is specialist and preparing the states with high fidelity, and they have some good results based on it. Another one, they can do it, they can, perform 4 or 5, even more, maybe 10 with the parallel with locality can be preserved. They can do it in space-like separation with a big number of it. But I think because they indeed do it parallel, they do not spec. It's not like you send a photon and then another one.
Same time.
Yeah, same time.
I mean, in principle, you could just set up many independent laboratories.
The problem is you have
everybody.
the problem is you have 10 lasers, good lasers.
Yeah, it's expensive.
But you are trying to do it. For sure, you cannot get huge amount. The epsilon cannot be really close to 1, but can go it.
Okay, we have two questions from the audience, from the online audience. So Kenneth, you can go first.
Hi there. Thanks very much for the talk. I wanted to try to go a little further. So let's take your conclusion as correct, that you have these options and of introducing weird correlations, and you have to introduce them all the way. You can't just go part way. You basically have to go all the way. So basically, what I wanted to discuss what would that mean if you have a parameter and you turn it and you have a robust control over another parameter. It seems to me that what you're saying is that going all the way, like not just having a partial relaxation, but a total relaxation, seems like you're saying there has to be a causal. It's not just a mere weird correlation. It's like almost like direct causal, where if you turn the settings and you can cause lambda, like a retrocausal model, then that's okay. Is that right?
Yeah. I mean, there are some people that they don't see any point on the results based on this kind of discussion because, I mean, if you give up of one of the hypotheses, why you should care if it is partially or completely? Some people say that, and I think it's okay to have this opinion. And
Well, what's your opinion? What's the difference between a partial and complete relaxation of these things?
I mean, I think it's interesting from the point because some people was wondering maybe it's just a bit of, for instance, just a bit of you lose just a bit of free will, and this would be the reason. So, but I mean, I don't know completely. I think it's do not solve the problem for sure. Like, okay, now you have a good answer of which one is failing. I think uh, it's still a big question. And what you have done was just to clarify. Okay,
Okay,
if
but
one
maybe
of
you
them
could,
fails, it must be a lot.
but you could maybe push the conclusion a little further, saying, well, if you have to fully relax one of these things, then you're basically saying there has to be a causal. It's not just correlation at that point. It's like it's causation, right?
Uh-huh. Yeah, I think for some of them, yes, like communication must be causation, right? All the time, it
Exactly.
must one choice must be causing something on the other side, and this must be true in all the rounds, something like
If you
that.
relax
Yes, yes,
particular assumption, right? And then if you relax measurement independence, it becomes a retrocausal conclusion.
yes, something like in these directions. Yeah,
Okay, thanks very much.
thank you.
Yeah, we have another question here from the in-person audience, and then I'll go back to Gleb.
Can you go back to the way you introduced the epsilon model again?
Yep.
All right, so this is one way you could do it. So you have the
Yes.
difference of these probabilities, but presumably there are other ways you can
Yes,
do it too.
indeed.
So I'm thinking of, for example, you could say rather than the conditional probability being 0 of the outcome independence, you could say the conditional probability of A, for example, given B, that itself must be less than some other parameter, delta. So I'm just thinking that there are other ways you could introduce these correlations into the model the way you did.
Mhm.
Have you considered those other ways, or is this somehow a privileged way of doing it?
No, you have considered other ways. I mean, as the results, I mean, from different ways, you have different parameters and this kind of thing. But for instance, you have considered as well, I think, mutual information or something like that, a more informational measure. And you were able to prove, I don't remember exactly now, but you were able to prove if you can relax one of them. I mean, if you are arbitrary relax one of them, you do also arbitrary relax the other and vice versa. So it can be, the result can be put in different ways to do this relaxation here. We'll have to also think about it. For sure, it might be other way that is not, the result will not be true, but you have to consider some variations.
Gleb, you're next up.
Okay. I wonder if these results can be interpreted as the impossibility to describe the wave function collapse in terms of probabilistic processes, like the hidden variables theory describes everything in terms of probabilities. But you showed that varying these correlations on the level of probabilities doesn't add anything to quantum correlation. So it doesn't reproduce quantum correlation, as far as I understand. And does it mean that this result can be interpreted as a kind of proof that wave function collapse due to measurement cannot be described purely statistically, like in terms of so it's something more than just playing the statistics and these outcomes and something like that. Like one cannot divide the boundary between the measuring device and measured system, something like that.
I think it can go in this direction, and maybe it's more related with this part here. Okay. To be honest, I don't completely understand it, but there are some people that say that when you add this variable here, you are already kind of assuming hidden variables model, and maybe it fails on this part. Although from mathematical point of view, we can always do it, but there are some people that say that this is already the step that you will not work anymore, because you cannot look for causal models, classical causal models, in the sense of classical variables here. And this is already the point where the stuff is not going work anymore. And I think it's, in some senses, in the direction of what you have told of. The statistics are not, I don't know, they cannot describe well what is going on in the quantum experiments. It should not use this formulation to do it. And I think it can be one of the interpretations of Bell's theorem in general. But I don't understand so much.
But yes, this is very interesting in the sense that means that on the quantum level, it's one more proof that on quantum level, the reality doesn't describe by probabilities completely. So it's like it has ingredients such as quantum phases and so on, which cannot have any probabilistic interpretation by itself. Responsible for correlation, for example, between measured system and measuring device, which you never can get rid of.
Yeah, I think it's like in this direction.
Questions, either from here or from the online audience?
Question.
So yeah, sure. The last question here.
So could you go to the slide where you defined L, the element dependence? Yeah, right. So it's just a question of what is the absolute value of X and Y?
Oh, sorry, it's the cardinality of number of measurements and number of cardinality. The number of measurements of Alice, the number of measurements of Bob. And then we have, because when L is equal to this quantity here, this is kind of the cardinality of these two variables, two random variables. And what I'm saying here that when this is bigger than 1 over the cardinality of the first variable and the cardinality of the second variable, the product of both, it's basically saying that this distribution here is uniform. Because it's 1 over the number of possible values of the
cardinality. So X is a set of
X
some
will
numbers.
take a number of different values. It's the measurement setting. X and Y are the measurement settings. So if you have like, you know, 2 possible settings here and 2 possible settings here, then this would just be saying, in that case, L would be a quarter. And since it has to be a probability distribution, saying that each of the values is greater than or equal to a quarter means that they all must be exactly a quarter. So it says it's a uniform distribution. So if L is anything larger than that, then you have some flexibility to change the value of the probability of the different values of X and Y.
So the limit of measurement independence is taken to be equivalent to the case is a uniform distribution.
Right.
Yes, exactly, yeah.
Is it necessary? Like for measurement independence, we only need X, Y, not dependent.
Yeah,
on-
it's
I mean, so this is what I was saying earlier, so
Uh,
I made the comment that this is assuming that you are implementing the experiment in such a way that you expect X and Y to be uniformly random.
I see. Okay, thank you.
That was a good clarification, yeah. Let's thank our speaker again. So thank you, Carlos. I assume that we will take Carlos for lunch to noon. Does that work?
In principle.
So
And there is a science forum talk today, but
so lunch at noon at noon, if that's okay. So I would try to do a reservation. So who is coming? Just a head count. No, so 3, 4, 5. Andrew, do you have?
Let me look at my schedule for today.
Sure.
also from.
Matt, we have a meeting at 1, right?
I know, but.
Okay, I'm just
Yeah, I
reminding you.
There should be
yeah,
45
yeah, I
minutes
can
in.
join.
So 1, 2, 3, 4, 5, 6, and perhaps Efrain.
What about you from his? I know he popped out, but.
I'll include
I don't know if
him.
you're
Yeah,
still
let's
ready.
include him too.
Include him anyway, yeah, and Thais in this case, but yeah, hate. So thank you, Carlos, again.
Thank you.
Yeah, thank you.
But you have to call, make sure that we can do the reservation.
I will.
As if sometimes Heidi doesn't happy if we do it too late, and so we go somewhere else if Heidi's unhappy with the large number of people.
Okay, okay, okay.
Also today, probably like sitting outside day, but.